To start, I need to give credit to Dennis Conti, who's not able to be here today. Dennis is the chair of the AAVSO's Exoplanets section and literally wrote the book on how to do exoplanet observations. If you've got any interest at all in observing exoplanets, I urge you to get a hold of Dennis's material. Most of the slides that you're going to see here today come from Dennis. So why do we bother with exoplanets? And the answer to that is that exoplanets touch us in a very personal way, because the existence of exoplanets get directly to the question of, are we alone, or are there other people out there? Is there a possibility of other people being out there? Is there a place other than the Earth where maybe people can thrive? Is it possible that there are planets out there that we could detect today with chemical signatures that tell us that, yes, life quite possibly does exist on these exoplanets? That's part of the reason that exoplanets are important to us as a society. And as we'll talk about here, it turns out that all of the fancy equipment that we've got in orbit doing dedicated exoplanet searches is unable to do the complete job. That equipment needs to be augmented by Earth-based observation, and the need for Earth-based observation completely would overwhelm the availability of professional resources to do it. And so the only path forward is to rely upon amateur observation of these exoplanet candidates as a way to get to the bottom of some of these questions. We now know that exoplanets are all over the place. Most star systems have exoplanets. We've seen evidence of exoplanets in multiple star systems. So there's really no reason not to have an exoplanet just about everywhere. One of the challenges putting this material together here for today was coming up with a consistent number of exoplanets that exist. This number changes week to week. Whether it's 5,000, whether it's 7,000, whether it's closer to 10,000, all depends on which source you look at. It also depends upon what criteria you use for declaring an exoplanet, yes, to be a confirmed exoplanet, or just a candidate exoplanet. Some of those exoplanets we can't see any evidence of, but in some cases, the exoplanet itself passes directly in front of the disk of its host star and blocks out some of the light from that host star. With care, and with a big enough exoplanet, we can detect that diminish in the star's light as a result of that transit of the exoplanet across the disk. However, as we'll see later, the amount of light that you lose due to the presence of the exoplanet varies with the square of the exoplanet's size. So knowing that detecting exoplanets as they transit is hard, detecting small exoplanets is hard squared, and makes it very difficult here from the Earth's surface to see things on the size of the Earth. However, there's a lot of exoplanets that are bigger than that, and a lot of exoplanet candidates that are good candidates for observation from the Earth's surface. We know, we've observed multiple exoplanets going around some stars. We have other stars where we've only got evidence to date of one exoplanet, but there are techniques we can use observing one exoplanet to possibly infer the existence of additional exoplanets around that star. And so the number of exoplanets that we're aware of is going to continue to grow over time just because of the number that are out there. The easy ones are where you have a really big exoplanet, a Jupiter-sized thing, that's in a very close orbit around its star. Because it's in a close orbit, you get frequent transits, and that makes relatively deep, relatively frequent dips in that star's brightness, and those become relatively easy to pick up. Where things become difficult is when you have a star that's in an orbit, to take an extreme like Pluto, where you've got Pluto's not a planet. Well, I'm old enough that Pluto was a planet, where you have to wait potentially hundreds of years in between transits of that planet in order to put together orbital data. I mentioned the multiple stars. Things get wacky when you have multiple stars and you've got planets that are introduced as an element of that system. Figuring out which stars the planet is orbiting around. Is it in a large orbit where the stars are doing their thing at the center, the exoplanet is way on the outside? Or is the exoplanet tied more strongly to one of the stars itself within that system? We know that there are exoplanets that are not attached today to stars. These become very interesting objects, both to understand how they got to that state. They're also interesting because they're much harder to observe as something not attached to a star. And then we look at our solar system, and things tend to make sense to us in our solar system, where all the planets are going in the same direction that the sun is and roughly sitting in the same plane. As you go out to other stars, you do find instances where things are not as nice and tidy as they are in our solar system. We do know that exoplanets come from the same material that stars are born from, the same material that the Earth was born from. However, planet formation, especially in terms of the location within that extrasolar system where the planet is formed, has a big influence on the orbit, has a big influence eventually on the composition of the exoplanet. And depending upon the dynamics of the system, we know, because we have been able to piece together what happened in our own solar system, that planets can migrate from one spot to another spot within the system. We have evidence here in our own solar system for three broad general types of exoplanets. We have the rocky kind of exoplanet, which is what we're standing on. We have our gas giant exoplanets, and we have our icy exoplanets. As we look to other extrasolar systems, we find the same three kinds of planets out there. We'll answer this question in a minute, but a thought question for you. How could we, here from the Earth's surface, distinguish among these three types of exoplanets as we look at what's going on in another system? If we can figure out its density, that gives us a strong clue as to whether we're looking at something that's rocky, something that's icy, or something that's primarily a hydrogen-helium mix. In order to calculate density, we need to know the size of the exoplanet, and we need to know its mass. Well, it turns out size is relatively straightforward for us to figure out, because as that exoplanet transits in front of its host star, we can measure how much the light dips during the transit, and that gives us an indication of the diameter of that exoplanet. By doing radial velocity measurements of the exoplanet, we're able to get information on the relative mass of that exoplanet. We can combine that mass estimate with the size estimate in order to get an estimate of its density. So here from using data that amateurs can gather, we get important clues that answer questions like, is that exoplanet something similar to Earth, or is it something very foreign to what we're living on? Most amateur work with exoplanets is done by looking at transits. Transits involve looking at the brightness of the star as the exoplanet passes in front. You get a light curve very similar to what you see down here at the bottom of the screen right now, where for some period of time during the transit, there's a reduction in the total brightness of the system. The amount of reduction for a big planet, a Jupiter-sized planet, can be as large as 1/100th of a magnitude. As you go to exoplanets that are smaller than that, you're now talking about thousandths of a magnitude drop, or even less than that. Nevertheless, as we'll talk about here off and on, that's within the realm, or some of that is within the realm of what we as amateurs can do. I've mentioned how we use the depth of the light curve to get an indication of the diameter of the exoplanet. We also use the shape of the light curve to tell us things about the orbit, tell us things about the host star and the behavior of the host star. We also can tell from the shape of that curve what the inclination is of that planet's orbit around the star to our visual perspective, line of sight to the system. So all kinds of information can be pulled from that. So how do amateurs get involved? For the most part, amateurs are not going to discover transiting exoplanets. Where amateurs get involved today is in taking candidate discoveries and being able to categorize them as either, yes, this fits all the necessary criteria for being a true exoplanet, or on the other side, saying we can pretty much rule this out. This reduction in the brightness of the host star that we're seeing is almost certainly not due to an exoplanet. And we'll have examples of that in just a minute. One of the things that I'm going to mention in a few minutes about the planning process for observing an exoplanet transit. One of the first steps in that is finding out when the transit is going to happen. Well, one of the realities of that is when you go pull that data, you often find really significant uncertainties in the prediction of when the next transit is going to occur for that exoplanet. And the root cause of that is that the community simply doesn't have enough observations on that particular exoplanet to have truly refined the orbital characteristics to the point where we can make accurate predictions months or even years in advance. One of the ways that amateurs can help is by going out and just measuring the timing on an exoplanet transit in order to refine those orbital characteristics and give us a better chance of knowing when the next transit is going to occur. False positives. We'll come back. This one's a cool one. We'll come back to that in a minute. Undiscovered other planets. The Earth does not orbit around the center of our sun. The Earth orbits around what we call the barycenter of our solar system. That is the center of mass of our solar system. That center of mass is displaced significantly from the center of the sun by our big planets, Jupiter and Saturn particularly. As we go in and look at extrasolar systems, and we start making very precise measurements of the timing of the exoplanet transits, in some cases we come to the conclusion that that exoplanet is not orbiting around the center of its star. That's a first indication that there's likely other stuff going on in that extrasolar system. By making those measurements precisely enough over a long time baseline, we can figure out where the star is over time relative to the center of mass of its solar system. From that, we can figure out what other planets are possible within that system. One of the most successful missions looking for exoplanets has been NASA's TESS mission. It has come up with thousands of candidate exoplanets. This is a mission that stares at regions of the sky for a period of time, looking primarily at the bright stars, and we'll talk in a minute about one of the design compromises in the TESS mission, which enabled it to be affordable and to be able to gather its data, but which leads to a lot of candidate exoplanet transits that need further observation. So we divide the sky up into a bunch of pieces. TESS goes, observes those sections of the sky, gathers brightness data on bright stars within that region, and looks for characteristic dips. There is a software algorithm that looks through that brightness data and looks for dips that seem to match the characteristics of an exoplanet transit. Those become candidate exoplanets. One of the primary purposes of TESS was to come up with candidate objects to use with the James Webb Space Telescope, which is capable of going in and measuring exoplanet atmospheric characteristics. TESS is not able to do that. So this is an example of one system serving as a source of objects of interest for the other mission. By far, what to me is the most remarkable thing about what's on the screen right now is the bottom set of bullets. That less than 10% of the total set of TESS candidate exoplanets have been able to go through the confirmation process and come out as confirmed exoplanets. It's not that the other 6,000 have been identified as non-exoplanets, as false positives. It's all sitting in the inbox, waiting for our community to get out there and observe it and gather the data that's needed to categorize these things as either confirmed exoplanets or non-exoplanets. So, one of the compromises that was made in the TESS mission involves the size of its camera's pixels. These pixels are big, and as a result of that, you can have, and one of the reasons for that is TESS is specifically focusing on bright stars. There aren't that many bright stars in the sky, so you don't need really good angular resolution in order to observe just the bright stars. However, what happens with these big pixels is you can end up with dozens, if not hundreds, I'll give you an example of that later, of stars that fall on one pixel. So when TESS observes one of these dips, that its software algorithm says, yes, that looks like an exoplanet, you have no idea which of those dozens of stars falling on that pixel was actually responsible for the dip that you see. The most common, far and away, most common source of these false positives have been eclipsing binary stars that happen to fall on the same pixel as was looking at one of the TESS candidate stars. So instead, so what we see is this little itty-bitty dip in the brightness of that pixel. And we get all excited because maybe that means that the bright star in the pixel got dimmed by an exoplanet. The reality is, in most cases, the bright star in the pixel didn't change brightness at all. What you had is one of these faint background stars that underwent a really significant dip in brightness because it's part of an eclipsing binary. That big dip, relatively speaking, on the faint background star ends up looking like a little dip on the bright star that we're looking at. So here we've got a very typical image. This is actually an exoplanet field. If you zoom in from this Earth-based image, you can begin to see individual pixels from our Earth-based camera. Now, if we superimpose on this a test pixel, it's the red square. And so all of that background detail gets lost as you go do this. What clues can we use? And these are clues that are easy for amateurs to identify. What clues can we use to identify the false positives from a real exoplanet transit? Well, one of them is up at the top, the shape of the curve. As you have an exoplanet transit across its planet's disk, during that transit time, you tend to see a fairly constant minimum brightness during the transit. When you have binary stars that are eclipsing each other, you tend to get a more V-shaped curve that lacks that bottom plateau. With exoplanets, there is no change in the system's brightness when the exoplanet goes behind the host star. And so we see one dip. It's always the same shape every time that exoplanet goes in front of its host star. With a pair of eclipsing binaries, for one of the dips, we have star A in the front, star B in the back, and then half an orbit later, they change places. And so it's very common, if those two stars are not identical physically, to have two different dip sizes as we look at the light curve of that system. And then finally, exoplanets passing in front of their host star don't change the color of the host star. When you have eclipsing binary stars, depending upon which star is in the front, which star is in the back, if those two stars have different colors, we see the system's color shift as it goes through those eclipses. And then finally, depth. If the depth of the light curve is too big, we can sit down and figure out what size exoplanet would have to cause that. And if the exoplanet size works out to be something on the order of 1/3 the diameter of the host star, we can pretty much pat ourselves on the back and say, that thing is not a planet. If it's that big compared to a star, it most likely is a source of fusion and is generating light of its own. So let's look at a false positive. Here we have the light curve that was obtained on one of these candidate test objects. So this is the first look at that light curve. What you see as you look at this is a light curve that, number one, doesn't have a flat bottom. It's kind of distinct there at the bottom. And number two, if you can see the numbers on the left, you see that the change in brightness is roughly 8/100ths of a magnitude, which is extraordinarily big for an exoplanet. So right now, this thing has two strikes going against it. We get a second observation of that system. one of the things that's key about this is the second observation occurs 11 orbits of the exoplanet later. That's an odd number of orbits. Again, we see similar kind of depth, similar kind of shape. If we superimpose the two light curves on each other, we see that the two depths don't match. So this is a strong indication. In fact, this is more than 3 strikes. So this one can be rejected as a true exoplanet. This turns into a false positive. What we're seeing is a background eclipsing binary that happens to fall on the same pixel as one of our bright stars that was the test target. So this is the kind of thing that amateurs can do. Some of the data that we just put up there is from the amateur community. Here we've got an image, again, of an exoplanet target. We've superimposed on that the list of stars that fall within the test pixel that become candidate nearby eclipsing binaries to potentially confuse, the light curve that we get from that candidate exoplanet. As you go look at the data coming from the TESS mission and the roughly 700 to 800 stars that have been confirmed so far, along with the stars that have been ruled out by being false positives, you find that a majority of that work is being done by the amateur community. One of the reasons for that is an exoplanet transit typically takes several hours. You may be tying up a telescope for 2, 3, 4 hours in an observing run. It needs to be pretty continuous over that period of time. And as Bert talked about earlier, it is hard to go get time on a professional telescope for hours at a time like that to look at something that may just be a false positive. Nobody is going to get a paper published and get their name associated with research on false positives. There is a very formal, rigorous process that we go through in order to confirm a candidate exoplanet as being a confirmed exoplanet and ruling it out. That process, although it's rigorous, has places in it for amateurs to contribute. And the last bullet is kind of interesting. In some cases, we have more observational data than has been analyzed. There is opportunity for amateurs to step in as analysts in order to help reduce some of the backlog that exists within the exoplanet observing community. Okay, what's it take to observe an exoplanet? I wasn't going to say how many times I have gone out to observe an exoplanet and missed the exoplanet transit by being out either at the wrong time, which is invariably caused by incorrect conversion from UTC to local time, or worse, being out on the wrong date because of incorrect date conversion from one time to another. In talking to other folks who have done this, one of the things that is common is that we've all taken a fairly disciplined approach to the planning process for going out and looking at or looking for an exoplanet transit. There's a bunch of different times that are important in doing that planning process. One of them is knowing when sunrise and sunset are as brackets on what you can observe. Another is knowing when the exoplanet transit is expected. Up here you can see that with the vertical blue lines. There are a number of resources that are available to give you exoplanet transit prediction times. Those are fed by all of the published material on exoplanet behavior, exoplanet orbits that have been pulled together. If you just go Google exoplanet transit prediction, you'll get the 2 or 3 key resources available online for doing those searches. You can do searches for a particular night. You can do searches for a particular location where you are. There's all kinds of criteria you can apply to help with that search process. Another time that matters for some of us, for me it does, is knowing when this exoplanet host star is going to transit the meridian, because I need to work a meridian flip into that planning process. And there are times when you don't want to do a meridian flip. You don't want to do a meridian flip during the ingress or during the egress at the beginning or the end of the transit. But doing a meridian flip outside of the transit or doing a meridian flip even right in the middle of the transit, those are fine times to go ahead and do that. You need to plan, recognizing that you need at least 30 minutes of data before the beginning of the transit and after the end of the transit in order to get a good baseline brightness for what's going on outside of the transit. And then finally up here, there's a green curve and a red curve that are indicators of where in the sky this exoplanet host star is going to be throughout the night. One of them, which one? The green one is showing the elevation angle above the horizon. The red one is showing the air mass, the thickness of the Earth's atmosphere you're looking through. When I'm doing this, I set a pretty firm upper limit of 2.5 air mass for the maximum I'm willing to try and do an exoplanet transit observation through. But for many candidates, the one I've got up here right now, that gives you almost the whole night if you're in a favorable part of the sky as you go through and do this. So once you've done your planning, there's the issue of what equipment you're going to have. This is a typical configuration for observing exoplanets. Here I think we've got an 11-inch telescope. I'll talk more about guiding in a minute. On a stable mount that is easily guided, one of your objectives is to try and keep the exoplanet host star roughly on the same pixel in the camera for the entire 2, 3, 4 hour duration of the transit. One of the things that you really want to minimize is data scatter. And it's a fact of life with today's cameras that you're going to have pixel to pixel variation. Having good darks and good flat calibration will minimize that, but if you can hold the star on the same pixel the whole time, you're going to get much less data scatter. Oh, filters. You can get good timing data on an exoplanet transit with no filters whatsoever. If you go in and use a photometric filter now, or multiple photometric filters, now you can go in and make meaningful observations about color and look for color changes during a candidate exoplanet transit in order to be able to rule out a candidate if you're seeing color changes in the host star. So I mentioned flats and darks. They're essential. If you need to be comfortable with that process. And as you're doing your planning, you have to make sure you've included the time in your plan for doing those master calibration images. And the bottom bullet, with care, it's not all that hard to reach the point where your measurement scatter is measured in thousandths of a magnitude, giving you a lot of different exoplanet candidates that you can go explore. One of the fun things about observing exoplanets is that the software for doing the light curve analysis is freely available. There are 2 good candidates that people are using. Actually, I'm sure there are more than these 2, but these are the 2 that I've worked with. Exotic, which is a product that comes out of NASA. AstroImage-J is another good one. They differ a bit in how the user experience is either friendly or not so friendly. And they differ in how much influence and control you've got as you go into the modeling process for what this exoplanet is actually doing and what it actually looks like. All right, so amateurs have a significant role to play in all of this. The AAVSO is a great resource for amateurs who are interested in doing exoplanet observations. And Bert talked about many of these things. We've got a section that's going to pop up here for specifically dedicated to exoplanets. So that's a place where exoplanet observers can gather and exchange tips and techniques for observing exoplanets and for going through that rigorous process I talked about to take candidate exoplanets and convert them into either confirmed or as false positive exoplanets. There are guides available on exoplanets specifically. The AAVSO has a number of products that are available, guides on how to do photometry, the measurement of star brightness in general. AAVSO has a mentoring program. Different people have different ways of learning things. If you're a person that needs to be able to, or benefits by talking through things with someone else, by all means, go explore the AAVSO mentoring program. AAVSO is also there to help coach you through the process of becoming an accredited TESS follow-up observer in order to go in and do that work. And so on that note, does anybody have questions? Yes?
You said you have 26 that are accredited. Well, what's the opportunity, so to speak? If you had 100 people or 200 people, is there enough data to fill all that need?
The inbox of stars waiting to go through that process is so deep right now, you could take every AAVSO member, turn them into an exoplanet observer, and you probably still don't have enough. Yes? So that practice of dithering is generally not helpful when you're going in trying to do precision brightness measurements. Instead, we rely upon having really, really good flats. And good flats are hard to make. But if you have a good flat, that is going to give you a more repeatable observation than you will get by introducing dither. If you're going to introduce dither, now you have to start averaging things over time in order to get rid of the variation that the dither has introduced. And as you do that, you lose some of your time resolution. And one of the things that we do want with exoplanet observations is to get really good timing data in order to refine the orbit. So we don't particularly like averaging those measurements together. So no, we don't do dithering when trying to make precision brightness measurements.
So does that imply that it's a little bit more challenging to do this in a remote observatory type situation? You pretty much got to have a flip flat and do flats either before or after a given imaging session, right?
The question was whether this need for really good flats and darks makes it hard to do remote observing. I know that there are observatories, because I've seen them, that are set up to do remote flats by having a flat screen that can be put in position in order to get a good flat on the telescope. Now, you're not going to have somebody running out there with a t-shirt to go put over the primary. But it is possible. It is a hassle if you're trying to do this remotely. I know even in my backyard observatory, where I try and stay indoors all night long, I did have to jump through hoops in order to rig up a system for doing flats. In the end, I found that my best flats are obtained during the day by shooting up at clouds. Yeah. So
Is it really important to get flats every single observing session? Or can you use a flat library? Or
So have I ever cheated and reused flats? Yes. However, I do find that those observing sessions where I sit back at the end and say, wow, I only have 2.5 millimags of data scatter on this, are the ones where I look back and say, oh yeah, I did a flat that night, and oh yeah, I did my own set of darks that night. So yeah, you can get away with it, but it also pays off. Yes?
Have you considered using either AI or an algorithm and what the feasibility of that is to see all that data you mentioned that are in the emails waiting to be analyzed?
So yes, there has been some work done on machine recognition of profiles, and that can rule out some stuff, but that can't solve the problem of multiple stars sharing a pixel, where you simply don't have enough information that's been downloaded from the satellite in order to resolve that question. So there you really do need to go in with a different camera, with a different pixel level resolution in order to gather the additional data. So there is work being done on machine recognition of exoplanet transit light curves, but it hasn't solved the problem. Yes? I don't know the degree to which that's being done. I'd be a little bit skeptical of that because there's so many things in the sky we look at and we just end up scratching our heads saying, this doesn't look like anything. So yes, yeah.
what's a typical image scale necessary to provide useful data? Do you have to have a C11 with a 2.4 micron?
No, it depends upon the brightness of your target. It depends upon how crowded the field is. I just try and match pixel size to seeing. The same kind of thing I do for my general purpose photometry. And as long as I have a decent match there, that works well for exoplanets.
Either way, it's going to be better than TESS.
Yes, it's going to be better than TESS. Yes? So atmospherics have a big influence. In a perfect world, I'd be good enough that I was able to get rid of all the systematic stuff and just be left with the atmosphere. One of the filters that's often used when all we're trying to get out of an exoplanet light curve is timing data is a blue blocking filter. Yet when you look through these things, they look kind of yellowish. By getting rid of the blue light, you cut down on scintillation effects, which are due to atmosphere. And by cutting down on that, you improve the precision of the measurement. So yes, atmosphere works into it. That's one of the reasons that we put these dedicated exoplanet survey missions outside the Earth's atmosphere, because they can detect much smaller variation in brightness than we can do here from the Earth's surface. What else? Yes? So how much aperture do you need? And I'm going to give you the coward's answer to that and say you need enough aperture to get a good SNR, signal to noise ratio. And you want a signal to noise ratio that's certainly better than 100 to 1, probably 300, 400, 500 to 1 is getting into the right ballpark. And the aperture that you need to do that depends upon the amount of sky glow that you're fighting. It depends upon the brightness of your target star. I use a spreadsheet to predict signal to noise ratio when I go off to observe a variable star, and it takes all that into account. You know, how much moonlight is there that night? How cold am I going to be able to get the camera? Because background dark current is a noise source. So you don't need an 11-inch scope. Now, there are people doing good exoplanet work with 8-inch scopes. I'm hesitant to talk about things smaller than that because I'm not sure I'm aware of anybody working with a scope smaller than that. But I'd say 8 inches on up is putting you in the ballpark of being able to do good exoplanet stuff.
Bigger picture, which part of the parameter space in exoplanets, I'm talking, mass, orbital parameters, the type of planet, is the one where scientifically amateurs can make the best contribution right now? I don't know the state of the field right now, the size and the density of the planet. Which part of the parameter space can amateurs best contribute to or amateurs take up?
So probably the easiest parameter for amateurs to significantly contribute data is time. Understanding the time of the eclipse, because that can be easily combined with similar timing measurements from other observatories in order to give a really accurate both baseline measurement of the orbital period and also to detect variations in orbit time. Because for some exoplanets that are in extrasolar systems that have multiple exoplanets, being able to detect transit timing variation is a strong indicator of the existence of other planets, and you can even derive some orbital information by looking at the nature of those timing variations. So time is the number one thing you get out of it. Certainly, exoplanet diameter is a fairly straightforward one to get out of there. But interestingly enough, neither of those two are involved in the test confirmation process to a great degree, which is focused on light curve shape, on color change in the system. And although those aren't necessarily giving you information about the physics of the exoplanet, they're important from the perspective of the exoplanet research community.
So the shape and the time.
Yes. Anything else? All right, I will be around. Feel free to come grab me and explore further if you want. Oh, yeah. And in case you haven't seen it, there is an AAVSO tent set up. Feel free to stop by and talk to any one of us that happens to be there at the moment you come up.
And we have 4 tchotchkes there.
What's that?
We have 4 tchotchkes up there.
Okay.